the introduction, Mike. Today I'll be introducing Cory Dean. It's my great pleasure to do this. And it's also a unique opportunity in this colloquium series. I'm sure all of you have attended previous ones. There's an introduction to the introduction. So what that means is I'll be giving a brief 15 to 20 minute discussion about some of the essential ingredients, features, theoretical tools, whatever is needed as a good starting point to understand Cory's great results and to take some of that weight off of his shoulders. With that, I'd like to thank the CIQC, and let's get started. So in the beginning, I'll give a brief overview of twisted 2D materials, the landscape of possibilities that are out there, and I'll state what we'll be specializing in today for the purpose of the introduction. I'll then review some important formalism. I know there's quite a diverse audience out there, and I certainly don't recognize many of the names, so I'm hoping that we have representatives from both the physics, CS community and the math community, and so I hope that this discussing some of the formalism will help us establish some common vocabulary. And then finally, I'll be motivating the study of twisted materials. So these are echoing some of the results and arguments that people had been making prior to the exciting findings and prior to the more recent experimental uptick in great results. And so then I'll quote at least one of those results as kind of a proof or a demonstration that this sort of reasoning did turn out to be fruitful. So 2D twisted materials. So what are these? So these consist of monolayers. So within a given monolayer, you have pretty strong molecular bonds. But between these two layers, let's say you took two of them, they're only coupled together quite weakly together by van der Waals forces. So this affords us some flexibility in terms of being able to sandwich these together, possibly with different angles, possibly with layers consisting of different atoms altogether, so different molecular chemical structure. And so for the purpose of this introduction, to keep things simple and brief, I'll be talking specifically about twisted bilayer graphene as our prototypical twisted 2D material. But other popular building blocks for these sorts of structures include the transition metal dichalcogenides and hexagonal boron nitride and structures composed of all of these things together. It's quite an exciting field in terms of the pieces, the puzzle pieces you have at your disposal. Some of the upshots, which I won't be able to get into today, but which I know we'll hear from Cory, and I'm very excited to hear about, are two applications. One is a more fundamental one in a sense. It's that these materials afford us tunable solid state quantum simulators. So we can, in an ideal case, have some Hamiltonian which we want to simulate and construct a moire system, a twisted system, which might approximate that for us. Now there are various caveats, and we'll hear a lot about those. But then the second application is in terms of utilizing these as components of quantum technology in terms of larger quantum devices. And so their tunability will play a huge role in terms of our being able to make these components do what we want them to do. With that, I'll hop into the brief promised review of band structures. So how do we proceed? Well, it turns out you can say a lot about the structure of the energy spectrum of a non-interacting Hamiltonian based purely on translational invariance. And that's the whole secret. So how do we obtain a band structure? Well, you start with a hopping model on a lattice. Now, you see over here, I've illustrated just a simple one-dimensional lattice. But in principle, this could be 2 dimensions or 3 dimensions. And for the twisted 2D case, it's obviously 2 dimensions. Now we have as many translation vectors A as there are spatial dimensions. The translation symmetry of our lattice is represented by a certain set of unitaries, TA 1 and 2. And these things mutually commute because we expect these translations to form an abelian group. And moreover, because they're symmetries, they commute with the Hamiltonian. Now, owing to the T's being symmetries, we know that their eigenvalues they're diagonalizable and they have these unit length eigenvalues. And we label these by K. Now, why does this turn out to be the form of these eigenvalues? Well, it's for the following reason. The quantum numbers, with lambda K, the eigenvalues of T, taking this form, it means that we can compose the T's and we have an abelian structure because the A's just add in the exponent. And now another thing to understand about these is that although these lambdas are these phases, they're labeled by a quantum number k. And it's useful to think about the space in which these k's live. Now, it's not completely obvious, but we know that these a's, say a1 and 2, define some lattice. Now, correspondingly, there'll be a dual lattice defined by vectors b1 and 2. Now, these b's come with a peculiar normalization. Typically, we don't have this factor of 2 pi in other dual lattice situations, but it helps to simplify the exponent up here. Now, with this in mind, we see that k immediately, the least redundant description of k is that k lives not in the real plane or anything like this, but on a torus. And the torus, going around the directions of the torus, is achieved by adding to k one of these two so-called reciprocal lattice vectors b. And so what have we reasoned? Well, we reasoned that we can take because h and t, the translations are simultaneously diagonalizable, we can label the eigenvectors of h by these quantum numbers k. And that's precisely what we've done here schematically. Now, without having to know any of the details of the Hamiltonian, this is the sort of thing we can obtain. Now, what can we say about graphene in particular? So graphene is going to be the starting point for a discussion of these twisted materials. Well, graphene is a bit more complicated than the 1D case or some orthogonal 2D case, and that has a pretty intricate and interesting sublattice structure. So the first thing to notice is that although we'd be tempted to claim that the translation vectors in real space connect nearest neighbors in the lattice, that can't be true. Because compare this yellow site and this blue site. If this bond or a vector in the direction of that bond were the translation vector, then applying it again, we'd end up in this absence of a carbon atom, and that's bad. So the only choice we have is to connect the yellows to the yellows and the blues to the blues. Now, doing this bipartitions our lattice into these two sets, and we call them A and B, and these are the two sublattices of graphene. On the right here, I've drawn, or haven't drawn, I took this from a great review article by Castro-Nito, RMP. It conveys a lot of information. One is it conveys the torus structure of the Brillouin zone, which is this hexagon in which the Ks live. Now notice it's not quite a hexagon because it has periodic boundary conditions. Notice there are only two inequivalent corners. This is related by a translation to this and to this. And I've also denoted those reciprocal lattice vectors B explicitly here. Now, up until this point, we haven't said anything about the energetics of graphene. Another wonderful feature of graphene is that half electron occupancy. So if you fill if at the natural occupancy at which graphene occurs, the low energy theory is described by two inequivalent Dirac points. Why do we call them Dirac points? Well, it's because their energy dispersion mimics that of relativistic Dirac particles. And so we have two of these inequivalent cones, as I'd hinted, and they're located at what we call the two values of monolayer graphene, K and K prime, and I've circled K there. So now that we have some of the language and the material architecture, now we can think about motivations for studying twisted materials. Well, actually, to start off, it's not quite a motivation, but a wonderful observation that is a set of observations that have been made over time. And it's that twisted bilayer graphene has been experimentally found to lie at the intersection of two seemingly distinct classes of phases, it's describable in terms of only a joint cohesive argument in terms of two descriptions of phases. Now, one is in terms of monolayer graphene itself. So of course, twisted bilayer graphene will consist of monolayer graphene. What's the essence of what are the key features of monolayer graphene that make it unique and tractable? One is that it has, as we saw, a simple and moreover accurate type binding description in terms of very few orbitals, in terms of very few hopping amplitudes. And moreover, it's been experimentally found time and time again, as you can find in the review article, that the low energy physics of graphene is very much described by the Dirac cones. So keeping only the Dirac cones and somehow truncating the energies above and below, we get a good description of a lot of experimental phenomena. Now, the other end of the physics spectrum, in terms of what people like to think about, are so-called correlated electronic phases. Now, these phases occur when interactions are a dominant part of the physics. It can't be understood in the absence of any interactions. Now, there are various routes here and various types of materials. One sort of behavior that people typically see in correlated electron systems are Hubbard model realization. So Hubbard model is a system with localized orbitals and large on-site repulsion. Alternatively, a very different type of phase arises in quantum Hall systems, and these are known as quantum Hall ferromagnets. Now, these, on the other hand, are completely describable by Hartree-Fock sort of mean field theory, and there are all sorts of other phases that are classified as correlated phases, including fractional Chern insulators, et cetera, et cetera. So this is all very exciting stuff. Now for the motivation. So why do we care about twisted materials? Why aren't we satisfied with monolayer graphene? I mean, it's a wonderful material. It's very clean and pure and robust. So what more do we need? Well, the answer is we want to study the intersection of these two behaviors, that of the monolayer graphene and the correlated electrons. But the problem with monolayer graphene is the bandwidth, i.e. the kinetic energy, doesn't permit it. It's simply too large. And because the local orbitals are big in these SP orbital systems. Now in graphene in particular, this can mean that the bandwidth can be as large as 10 or 20 MeV. I believe it's 18 specifically. And that's a problem, because if we perform a crude estimation of the Coulomb scale, which we might estimate as just charge squared over the average distance between electrons, so basically the monolayer lattice constant, may be divided out by a dielectric constant, we end up with something like one or a few EV. Sorry, I misspoke. Now, at least U is not dramatically larger or on par with the bandwidth, and so we don't expect to see that the physics are going to be dominated by the correlated behavior. And so, right. So, what if a couple of things I've sketched here are on the right here. We have a depiction of a Moiré pattern, which we'll talk about in more detail for bilayer graphene. And on the bottom. So what is the main motivation for studying twisted materials is that if we had some monolayer band structure, suppose honing in on a single band, we look at something like this on the left. Turns out we can get a lot of mileage out of applying a periodic potential to the system. So a potential which breaks the discrete periodicity of the system into some smaller subgroup. And so that will correspond to our larger translation vectors and correspondingly a smaller space of crystal momenta. Now, obviously folding isn't going to be enough. So folding is just saying, well, instead of at every K having some certain number of energy eigenvalues of the Hamiltonian, I'll just decide that each K is going to label more than some integer, in this case, 3 number of eigenvalues. The folding won't change the bandwidth. But what will is applying a periodic potential. Here we can just look to Ashcroft-Merman's simple solid state physics, in which the application of potential opens up gaps at the edges of the Rowan zone. And so we end up, after the application of the periodic potential, with bands which are narrower than before. Now this leads us to the discussion of Moiré superlattices. What do Moiré superlattices have to do with this desirable property of some long scale periodic potential? Now the answer is, you can intuit a lot of it purely visually. Purely geometrically. Now what you do, and we can consider the sequence of images at the bottom of the screen here, are to consider 2 initially completely aligned layers of graphene. Now you can't distinguish one from the other, they're completely coincident. And you can start to continuously twist one in relation to the other. Now the third one you can kind of see at the corners here, the 2 hexagonal sheets of discernibly rotated relative to one another. And we see, if we were to do this in some sort of movie, that these bright spots shift as a function of time continuously. And what do the bright spots correspond to? Well, they correspond to the coincidence of certain carbon atoms in the top and bottom layers, because when carbon atoms are coincident, then so too are the spaces in between them, in the middle of their hexagonal cores. And so we see light, I guess, passing through this film. And then in the third case, and where we see dark spots are the opposite, where carbon atoms occupy the empty space between the carbon atoms and the other layer. Now this imposes a superlattice potential on our problem. And so we can describe these physics in terms of the Dirac cones of the 2 otherwise decoupled layers of monolayer graphene, and then a periodic potential V on the scale of the superlattice, which both has in-layer tunneling components and also crucially tunneling between the 2 layers. How does the diagram on the top right relate to the discussion we had on the previous slide about folding and then applying a periodic potential. Well, what we see on up there are the Brouillon zones, the monolayer Brouillon zones, red and blue, corresponding to the top and bottom layers. Now, in the case that, so what do what do these small hexagons correspond to? Well, that's the the so-called mini Brouillon zone corresponding to the superlattice, larger superlattice, smaller Brouillon zone. We say we have a commensurate situation where we can fill the volume of an original Brouillon zone with some integer number of the mini ones. And it turns out that even though this isn't always possible, it serves as a good guide for, in practice, computing observable quantities. There's no real distinction that people have found between the commensurate and incommensurate situations. So we'll just kind of think in terms of the commensurate one. And as I mentioned, the crucial feature of the Moiré potential is that it hybridizes the two layers Dirac cones. So we see in the bottom right here is two otherwise, so here we have two unhybridized Dirac cones. We'd imagine the presence of the Moiré potential. We can open up gaps, say here, between the two Dirac cones, and that can correspond to a small bandwidth, as we illustrated in the previous slide. Now, I was playing a bit fast and loose before. This whole story of a Moiré potential isn't quite sufficient. It actually requires, in the case graphene, some special features. Now, these features, intuitively speaking, have to do with the tendency for the AB regions, so the regions where the dark regions of the Moiré pattern to expand, be more energetically preferable locally compared to the AA regions. And so this leads to some variation in the tunneling compared to whether you're tunneling in one of these AB superlattice regions versus AA. But it's a complicated story and we don't need to get into it. Luckily, various people have performed important numerical studies. Bistritzer and McDonald were the first ones to do this sort of analysis carefully. And what they found indeed was something like we're seeing on the right. Now this analysis was performed by a separate group. We see as a function of twist an exceptionally small bandwidth on the order of a few, or maybe at most 8 MeV or so. Now, if we compare this to the Coulomb scale computed at the most promising of these angles, that's something like 30. So we find ourselves in a regime where the Coulomb scale is dominating. And this wasn't just conjecture. In the end, it turned out to be a good prediction of not necessarily particular correlated phase realizations, but it pointed us in the direction, pointed our experiments in the right direction. And what we found in the case of twisted bilayer graphene in particular, and this is in the Pablo Herrera group at MIT in 2019, was the observation of various glorious phases in twisted bilayer graphene. And that included certain metallic behaviors, unexpected superconductivity, and that were separated by insulators of an unknown origin. So with that, I would like to spend the last minute introducing today's speaker, Cory Dean, who will take on some of these topics that I introduced and provide great insight into them. So Professor Cory Dean is a professor at Columbia University. After doing a master's at Queen University in Canada, he went to McGill, where he joined the Gervais group, and he completed his studies there in 2009. Following that, he joined Columbia as a postdoc, 2009 to 2013, became an assistant professor at the City College of New York, and following that, he rejoined his postdoc location at Columbia, where he's been ever since. Now, his research is focused on a whole variety of things: fundamental studies and technological applications of solid-state devices, which he's going to talk about today, and over a span of various van der Waals materials in particular. Now, for this work over the last few years, he's been recognized via a variety of awards and fellowships, including the Packard Foundation Fellowship, the Sloan, and even the Presidential Early Career Award for Scientists and Engineers. So with that, I'll pass it off to Cory. Thank you for your attention.
Thank you, Stefan. I'll see if I can share my screen. Let me get started here. Okay, you can see my screen?
Yes.
And you can hear me okay?
Yeah.
And can you see my pointer?
Yes.
Okay, okay, thank you. Thank you so much for that wonderful introduction, and thanks for setting up this talk today. As you said, what I'll be talking about, the title of my talk is Twistronics with Real-Time Control, and I submitted an abstract describing some of the physics I'll be discussing today. What I realized discussing with Stefan and Charles in preparation for this discussion is that this audience maybe is a little bit broader than I had originally thought. So I'm going to amend my title in real time because I have real-time control over my talk. And I'm going to rebrand this as a slightly more broad talk, which is more about the general opportunity of designing quantum materials using 2D materials as a platform. So I think there's a lengthy discussion at the end, or opportunity for a lot of discussion at the end. If anybody has any, unless this violates rules that you've set out, if anybody has any questions throughout, I'm very happy to sort of stop and address questions in real time. So however you want to moderate that or hold at the end, it's up to you. Okay, so Stefan gave a really sort of nice introduction to this talk, a little bit from the perspective of a theorist. So let me approach this a little bit from my perspective as an experimentalist. Generally, what I'm going to be talking about today is what is the interest in my lab, which is understanding the electronic properties of materials and how to control those properties, really. So when we say material, we have some chunk of thing. And what we know, because we know a little bit, is that these materials are made up of atoms. And what I really want to know is if I put electrons in my material, or if there are free electrons available, what I'm generally really focused on in my group is how do these electrons move throughout the material? That's kind of the primary question. So I want to, have some understanding of how electrons are going to respond to stimuli, what the electronic properties of the material are, et cetera. Okay, so I'm going to take even a further step back from the introduction that was just given and ask the very simple question, how do electrons move in free space? And this is something because I'm teaching first year physics right now. Many of you, I'm sure, even in a high school level, have some familiarity with this, which is electrons are charged, you put them in the presence of an electric field, and they accelerate in the direction that the field pulls the charge. Now, what I'm interested in is not the free electron. So a free electron is going to behave like any other particle. It's got an energy momentum dispersion. The energy will go with the momentum squared, et cetera. What I want to know is what happens when we put the electron in the presence of a lattice. So here you might, if some of you out there, if you've taken no physics, probably that isn't anybody, but on the odd chance, if I asked you, how does an electron move through a lattice? A reasonable guess might be that it behaves something like, this game Plinko, they might be familiar with, or some kind of hard object moving through some scattering points. And that's a reasonable guess, but it turns out that's wrong. And it's wrong because of quantum mechanics, really. So electrons are not point objects, they're waves. And when these waves move through a lattice potential, basically there's an interference between the electron wave function and the lattice grating, really. So this is the sort of theory of conductivity that was worked out by Bloch and is the underpinning of what Stefan talked about at the beginning. And the idea is that exactly how this electron wave function interacts with the specific lattice, the particular nature of the interference that occurs, gives rise to a modified energy dispersion. So this electron no longer behaves like it's in free space, but it behaves like it's sort of modified. And this is the undergirding of what we call the kind of band theory of solids, which again was introduced a moment ago. So what I want to do at this moment is just sort of identify that there are sort of big three categories of materials from this perspective. There are metals, semiconductors, and insulators. And basically all of these have some kind of band structure. And the relevant feature of this band structure is that there's a gap, defines an insulator, or there's not a gap, or the electrons fill the band away from the gap, defines a metal. And a semiconductor is somewhere in between there where there's a gap, but the gap is small relative to ambient temperature scale. And the critical part here, which was discussed beautifully a moment ago, is that this is a very simple cartoon. The reality of what this band structure actually looks like depends in very specific detail in ways that were just described on where the atoms physically exist in space. So to give a very simple example of that, graphene is almost as simple as you can get, but more traditional material might be something like silicon or gallium arsenide, standard semiconductors. So here I'm showing gallium arsenide. And on the left is the gallium arsenide lattice picture, crystal structure, sorry. And on the right is the band structure that you calculate if you consider this fairly simple crystal structure. So you can see that the band structure is extremely complicated. There's many features to it. And depending on where you are in this band structure, you might imagine there are a wide variety of behaviors. But if you're a material, if you're somebody who studies like, electron transport in the system, all you really care about is what the band structure looks like around the energy level where your electrons reside. And in gallium arsenide, that's sort of right around this point here. So if I were to hand you a piece of gallium arsenide and ask you to measure its electronic properties, you would identify probably that it's a semiconductor, and your electrons are residing either in the hole band or the electron band, kind of depending on how specifically it's prepared. But the main point here is that all of this complexity comes out of a very simple picture. Where are the atoms in space? A kind of more stark version of this is if we think about carbon-based materials. So this is now a very simple system. So in carbon-based materials, we have only carbon. In the previous, we were thinking about two different types of atoms. Here, there's just carbon. And these can come in different forms. And what distinguishes them is the precise crystal structure that the carbon atoms arrange themselves into. So graphite, for example, has a layered crystal structure, individual carbon layers separated by gaps, these really sheets parallel to each other. Diamond also made purely of carbon, just the carbons rearranged into this kind of diamond structure. And just taking this single kind of atom flavor and rearranging it can give you very different behaviors, even in the broad class that we talked about. So graphite is an excellent conductor. Diamond is a nearly ideal insulator, one of the best we have. And we can realize this transformation, the point I'm trying to really emphasize, just by rearranging precisely how the atoms are kind of located. So that gives a hint towards what I want to really talk about in the remainder of this talk, which is, can we think about how we can engineer materials, electronic properties materials in particular, by gaining some control over where we locate the atoms of these lattices, really. So if you're a material scientist, what you'd like to do ideally, I imagine, is you'd like to have a machine that would allow you to take a carbon atom and locate it at a vertex of choice, and take another atom and put it exactly where you want it, and take a third atom and put it exactly where you want it, and so on, and build up a lattice that way. The problem is, if you're going to design a lattice in that way, you have the issue of like thermodynamic considerations. These lattices may not be stable. The atom-atom interactions and how that's mediated by the electrons may not want to arrange in the way that you want them to arrange, and so on. So the challenge for me, at least the challenge I'm setting up for this talk, is how close to that can we get? Can we design materials from the ground up? And there's interesting sort of opportunity there in these carbon-based materials. So as I said, I'm going to focus most of these are all the variety of allotropes of carbon that you can sort of realize. I want to focus on this this graphite system. And what I want to identify is that graphite comes to you, you find it in nature basically in a layered structure. But what we've learned how to do is how to peel off a single sheet and isolate it from the bulk of the graphite. And we look at its crystal structure. This is this honeycomb structure, as was just described. And already graphene behaves very differently than graphite. It's its own material. Really, in general, 2D materials tend to be quite different than 3D materials for a variety of reasons. I'm not going to sort of relitigate this, but graphene has been branded by many the wonder material of modern times. It really has, extreme properties in almost every direction that you might want to look. For the purpose of this discussion, I want to think about the electronic properties of graphene, as was introduced. We have a rather unique band structure here. Around the energy where the electrons reside, the Fermi energy, around that point, there's a linear band structure. And you might already kind of suggest that this band structure puts it slightly outside the classes of materials that I discussed a moment ago. It's not really an insulator or a semiconductor because there's no true gap in the system. And it's not really a metal, you might not say, because the Fermi energy tends to exist right at this crossing point, where at that crossing point, the density of states, theoretically anyways, is zero. So for that reason, graphene is sometimes called a zero gap semi-metal or some version of that. So it's kind of its own thing. The fact that it has a linear dispersion is also rather unique. That gives it certain properties I'm not going to go into too much, but they kind of stand out from a more more usual material that we're familiar with. Okay, so as I said, what I want to study generally is transport. So if there's any mathematicians out there or otherwise who have never done a transport experiment of any kind, I just want to make sure we're on the same page. So that page is that what I really mean is I apply a potential across my material and I measure how easily the electrons move through the material. I measure the resistance of the material really. And graphene being two-dimensional is interesting in that unlike three-dimensional materials, we can dynamically vary the amount of free electrons that we have in the system. And we do that through gating. So we make graphene 1 hour of a capacitor, we charge the capacitor, and then the number of electrons that are free to move in graphene becomes controllable. So here I'm looking on the left at the sort of typical band structure that you would have. And what I'm coloring here is the filling of this band structure. So for some gate bias, the most energetic electron is down at the top of this blue band here. And I'm going to measure resistance while I vary my gate bias, which means while I vary the filling across this band. So I'm first going to fill the system. I'm going to add electrons to it. And when I do so, I measure how the resistance responds. And what you see is that the resistance is very low. That's because graphene is an excellent conductor. But the resistance grows to some large value at zero bias. And that happens not because I'm necessarily introducing any disorder or anything like that. It's just that I'm squeezing it down to becoming nearly a semiconductor or nearly an insulator. There's very few density of states available at this crossing point here. And because of that low density of states, in a sense, resistance goes up. But I can continue to gate this, and what happens is now I recover a low resistance state, et cetera. So here, what's interesting about this material, because it's a semi-metal, out at finite bias or at high densities, it behaves very much like a metal, low density, et cetera. But on this side, our metal is full of conducting electrons, and this side, the metal is full of conducting holes. So that's also kind of a unique situation to have access to. Okay, so how do I actually isolate this monolayer of graphene? So this is the famous Scotch tape method. What we literally do 15 years after the first discovery of this technique is the same. We smear some graphite on tape. We so-called exfoliate the tape, and we smear that tape on a surface. And when we pull the tape away, magically, if we use the right tape, we're left with graphene on that surface. So the real breakthrough of like Novoselav and Geim and kind of the first publication was to note first that this technique works, and second that it's very easy to find the graphene. And we do that through this optical interference technique. So if I smear that graphene on a well-prepared substrate, and that substrate is typically silicon, which is conducting, covered with a specific thickness of SiO2, then there's an optical interference effect that happens here that gives you sort of visual contrast. And that visual contrast you can correlate to layer number. So the faintest color you see here literally is one atom thick, one layer of graphene. The slightly darker color is 2 layers, and then 3 layers, and so on. Okay, so as I said, that somehow remains the gold standard. You find a piece of graphite, you exfoliate it, and you can get a monolayer of graphene. You can put contacts in that graphene, you can measure the transport properties, and you can do all of that in the course of a day, even with no prior training, probably, which is one of the really amazing things about this field. In the past 15 years, what have we been doing? So one thing we've been doing is learning that, learning to appreciate that there are a wide variety of van der Waals materials, not just graphite. And by van der Waals materials, I mean materials where the structure is layered such that the interlayer coupling is weak van der Waals bonding, but the intralayer bonding is much stronger. All these materials share the similar property that they are, quote, exfoliatable. We can isolate a monolayer of each of these materials in the same way that I just described. And we can put contacts on those monolayers and whatever. And the amazing thing here is that the van der Waals material, the class of van der Waals materials span really all material properties that we really know about as far as we know. So not only are these materials metals, insulators, and semiconductors, but they have all manner of other properties. Some are magnetic, some are superconducting, some are topological insulators, and so on. And what's really amazing here is that, we can isolate each one of them and study them in their own right. But because we know how to sort of, peel off a single layer, it immediately motivates the idea that we might be able to use this to realize a version of what I described before, which is, can we take these individual layers and build new structures out of them? So in a cartoon way, you might imagine that I start with some material, maybe that's boron nitride, and some other material, maybe that's graphite, and maybe this is a transition metal dicalcinide. And I take some number of layers off of each, and I just interleave these together to form an entirely new crystal. So I indicated that, one goal of a material scientist might be place atom by atom where every atom of your system is. We're not quite there with what I'm describing on screen right now, but it's a close version of that. So rather than atom by atom, we can layer by layer build up basically arbitrary structure. And as I said, these can have all different properties. So what we can really do here that's really quite profound is combine really arbitrary material properties into a single structure. Okay, so how do we do that? As I said, I'm an experimentalist, so a good part of this talk will be sort of focused on the experimental opportunities and limitations. The way we do this is using a technique that we developed back when I was a postdoc, so like more than a decade ago now, which we call mechanical transfer technique. And the basic idea is that we have some kind of polymer, and we can kind of melt that polymer onto one of these materials. And the image what I'm showing is boron nitride. Then we can pick that boron nitride up, and we can press that really as sort of like a stamp onto another 2D material. And the amazing thing here is that even though the van der Waals forces tend to be weak from a kind of bonding perspective, they can be strong enough that we can sort of pick and peel these materials one after another and really build up a stack in sort of cartoon way, as I just described. So here's sort of an animated version of what that looks like. This is really not far off from reality. I've got some kind of polymer that's flexible, and on that I have put a thing I can sort of melt. That's the red layer. I heat and melt that onto, say, a boron nitride flake. I pick that up, and then I can use this to pick up a graphene flake, for example. And then I can place this down on another BN flake, and then I can melt away that polymer and make an encapsulated device, just like that. So as I said, this isn't that far from reality. Here's some real images of devices made in exactly this way. So the left is a top-down image of what we call a stack consisting of boron nitride, graphene, boron nitride. And in the middle is a cross-section TEM image. So these are imaging edge on the atomic layers of the structure. So the top few layers are boron nitride, which is a layered material. The slightly brighter layer here is a layer of graphene atoms, and then like monolayer graphene, and below that another BN layer. We can do this with all of the other 2D materials. So here's another heterostructure made in a similar way, integrating, in this case, BN, MOS2, which is a semiconductor, BN, etc. Okay, so this suggests like a really, in my view, amazing opportunity. We can design entirely new structures that you can't synthesize chemically, you can't grow by MBE or not easily so far, but you can easily do this by this kind of mechanical layering technique. So the image that was suggested by a review by Andrew Gahn a bunch of years ago is to view this system really as like, Lego blocks. So you imagine you reach into your bin and you grab whatever Lego you want and you just stack these things one on top of the other. And again, I think that's not very far from reality in terms of what we can actually achieve in the lab now. Okay, so this is all fantastic. We can make new materials, we can combine properties and so on. There are details that matter here. So as we said, the properties of material are really dictated by band structure, and band structure is dictated really by atomic lattice. And what that means is that, when we put atoms, layered systems together, they form a new kind of structure. And the overall property of the structure isn't going to purely be just how do we combine properties, but how do the electrons move through the structure? Where are the atoms in the structure? And one thing you notice is that if we do what was sort of the early days, if we put graphene and boron nitride, graphene and boron nitride have nearly a matched lattice constant. It's not exactly matched, but it's close. So what that means is if I look sort of top down, so here's my graphene band structure, cartoon image top down. If I place boron nitride on top of that, or below it, what you see is that a Moiré pattern develops. And the Moiré pattern results from the slight lattice mismatch, lattice constant mismatch between these two materials. Now, the relevant thing here is that the Moiré lattice, it turns out, acts like another scattering potential in the problem. So the electrons move through the graphene, they scatter off the graphene atoms. Now they see additionally this Moiré superlattice potential that has a sort of a longer wavelength than the underlying atomic lattice. And the consequence of that is to modify the band structure. And what's interesting here is that it does so in a predictable way. And you can imagine that, basically what happens is what was a linear band structure graphene becomes sort of, modified here. New features emerge. And these features that emerge occur at a position in energy in the band structure that is inversely related to the size of the Moiré superlattice potential. So what that means is if I rotate this graphene BN system, I can modify the size of the Moiré potential. And when I do that, what I do is I shift where in the energy band structure I'm really modifying, I'm really imposing this kind of like satellite, what we call like satellite Dirac codes in the system. Okay, so if I rotate back and forth, I can shift around where in the band I introduce these kind of new satellite features in principle. Okay, so this is now suggesting that we have access to an entirely new degree of freedom that's beyond just putting these materials together. So I place graphene on BN, I have a moire potential. That moire potential modifies my band structure. But now I think if I can controllably twist these layers, I can add further control over how I'm actually kind of modifying my graphene band structure. Okay, so the wavelength of the moire is a simple function of the twist angle that arises from the lattice mismatches, et cetera, and you can write that down. The question is, does this really happen? And the answer is yes, it absolutely really happens. So here's some STM scanning tunneling microscopy imaging of graphene on BN. And what you see here is real space imaging. This is topography imaging. And these honeycomb structures that you see are not atomic lattices. This is the moire lattice that's being imaged. In this case, it's graphene on BN. And as you go through A, B, C, D, what's happening is the twist angle is decreasing between the graphene and the BN. And what you're seeing is that this moire pattern is getting bigger and bigger, just as we predicted in the sort of cartoon image in the slide previous. Okay, so now if I try to measure transport in the system, what do I see? So remember previously we saw that if I measure graphene transport, I've got a peak in the resistance when I'm at the crossing point. In this system, what we say is that there's the initial crossing point, called the Dirac point, and then it's some energy away from that, as I showed in the previous slide. There's what we call a satellite Dirac point, or in density of states below here, there's a zero density states at the native Dirac point, and then a second zero density states at some higher energy satellite Dirac point. And so now if I measure transport in this system, what I see is not a single resistance peak, but 3 resistance peaks. And those correspond to when I move my chemical potential or my Fermi energy from this point to this point. I'm drawing only half the structure. There's an equivalent satellite Dirac point on the other side of the charge neutrality point. Okay, good. That's great, but there are some surprises. So the picture I draw here is fairly accurate from a simple band structure calculation point of view. What you notice here is that the actual, like the kind of like angle of the dispersion is expected to change a little bit, but otherwise this remains a well-defined massless Dirac system at the zero energy point. And the bulk of the sort of modification of this is expected to be out here. But when we perform an actual measurement, what we find is that, in fact, coupling between the graphene and the BN opens up a large band, it opens up a band gap in the system at the charge neutrality point. So we don't retain this sort of closed crossing point. Instead, actually, you can say the system develops a mass term or a gap opens here. Okay, what we find is that that gap is, it's not huge, few tens of MeV, but that's measurable at low enough temperature. And what we find is that the size of that gap depends on the angle. So now we have the ability to not only kind of distort a little bit the graphene band structure, we actually are turning it from a semi-metal into a semiconductor. It's really what's happening. And the size of the gap of that semiconductor is angle tunable as you vary the graphene BN orientation. So this is actually like, I think a pretty like if you've never done some material science, that's a pretty substantial statement. So we're taking a crystal, we're not heating it to extraordinary temperatures and not applying, massive pressure or massive strain. We're simply kind of varying the rotation angle between these two lattices and dramatically altering the most basic sort of characteristic of the system. Okay, so that's a hint of things to come, I guess. In that discussion, I'm talking about what happens if you place graphene on BN, where there's already a lattice mismatch. What about if I place graphene on graphene? So this is what was also discussed during the introduction. And as was nicely said, if I place graphene on graphene and I make them intentionally aligned, then from the perspective of how these lattices interfere with each other, there isn't much happening. One atom is sitting directly on top of the atom below, and you might imagine that electrons moving through the system see kind of a two-layer version of graphene, something like that. But now if I twist graphene one to the next, now what happens is in the two-dimensional space, now I get a moire pattern because now these lattices are not rotationally commensurate anymore. and small incommensurabilities in the rotational alignment mean that I have a periodic sort of structure over which the lattices go in and out of commensurability sort of locally. So now this is another way of imposing a more a superlattice potential. Again, the wavelength of the superlattice potential is angle dependent. But in this case, case of two-layer graphene, something really rather remarkable happens. The origin of this was described, thankfully, before. The kind of end result is that in the system, you get a flat band. And we can talk at the end, maybe afterwards, about our understanding of exactly where this flat band comes from. But the remarkable thing here is that this band is really flat if you're at the right angle. And really flat means like a few MeV. Which means the energy dispersion of the band is flatter, can be so flat that the kinetic energy is less than the Coulomb energy in the system. So that's really interesting, as was said before, because if you can get yourself into a situation where Coulomb energy exceeds kinetic energy, then the properties that such materials can have can become even more interesting than the kind of native class of materials that we discussed before. So whether something is a metal or a semiconductor or an insulator is what we call kind of a single particle character. Each individual electron behaves as if it's in a system that is one of those three. When Coulomb energy starts to dominate, then new correlated phases can emerge. That can be things like superconductivity or interesting magnetic order or interesting correlated insulating states, interaction-driven insulating states, etc. Okay, so this system is supposed to be a flat band system. Is it, and does it host these any interesting properties? And the answer is absolutely yes. The system absolutely is a flat band system in the way that was sort of anticipated by the early theoretic work of, for example, Al McDonald. And it turns out when you measure the system, it's remarkably unique compared to measuring graphene in any other configuration. So two of the things that pop out in the first experiments are that one is that it superconducts. Until very recently, it wasn't identified that any other form of graphene had any kind of superconducting phase. Certainly the origin of superconductivity is driven in some part by the interactions scale that Coulomb interactions are dominant in this flat band system. The other is that you have a correlated insulator and half band filling. So this is what's called a Mott gap. And what's really amazing is this system is electrostatically tunable. So you can just shift the chemical potential by gating because it's a two-dimensional system. You can just with a gate shift from the Mott gap to the superconducting state to the kind of normal metallic state, etc. So that is also kind of rather unique amongst materials that host these properties otherwise. More conventional heavy fermion systems or cuprate systems, etc. Generally, you vary the number of free carriers by switching out atoms. You substitutionally dope the system. In this case, you don't have to modify the lattice at all. You simply add or remove electrons through a sort of gating technique. Okay. So that gives a really sort of great degree of control and tunability of these systems that generate a lot of excitement right away when this was reported a couple of years ago. Since then, as I said, we have access to a whole class of materials. We can investigate similar physics in these others as well. The transition mode calcinides are interesting because of a number of reasons. One is that they're different from graphene. They're not linear, necessarily like linear dispersion Dirac systems. They instead are semiconductors with a proper mass in the intrinsic state. And so now if you place one transition metal dicalcinide on top of another, now you have basically the interference between two massive systems. And these systems, again, you can get a flat band that emerges, but the nature of this flat band is a little bit different than it is in just a bilayer graphene. Also, these systems can have strong spin-orbit coupling, which graphene doesn't natively have. And these systems can have other properties that graphene doesn't have. So they can be natively ferromagnetic, for example, or anti-ferromagnetic, and so on. So what's been happening in the past few years is people have been exploring this space sort of one by one. Place material A on material B and see what the electronic properties do. Try to vary the size of the moire pattern and its magnitude, its depth, by combining different materials together. So you can choose different lattice constants and you can rotate, etc. One of the kind of really amazing things that recently has come out of studies of, I'm just showing one example of that here, of the TMDs, is the identity that there's a complex network of insulating phases in these systems. In addition to the half-filling Mott gap, there are a number of charge density wave states that emerge. This is all driven by interactions because, again, there's a route to engineering basically a flat system in these heterostructures. Okay, if you take a sort of glib summary, I can take 2D materials, I can make new materials out of them, and if I pay close attention to how to control the lattice mismatch through choice of material or through twisting, then I can basically create any phase of matter that we know about. That's my claim. I mean, that's been demonstrated over the past few years, which means these material systems are just phenomenally promising systems for doing, quantum research. So, why is this not the end of my talk? Oh, one more thing I should say. So this, the kind of benefit of this was perceived by many in the past years, but there's this nice paper by Kaxiris from Harvard, who sort of coined this new term called Twistronics. And the idea here is that because these materials have sort of small interfacial forces, you can imagine that you can sort of arbitrarily twist them one relative to the other, and in doing so, have a knob that you can tune to really like set the property to be what you want just by varying the twist. Okay, as I said, this is a profound opportunity. So, that's it. Good. We can all just go off and make the devices we want and start building quantum computers, et cetera. But there are problems, obviously. There are, let's say, challenges. What are those challenges? So in the case of twisted bilayer graphene, this flat band condition emerges only at a very precise twist angle. That's called, it's been sort of referred to as the magic angle. And here what I'm plotting is the relationship between the Coulomb energy in red and the kinetic energy in blue. And we might define the band as flat by some definition, we might argue is the range of angles over which the Coulomb energy exceeds the kinetic energy. So we see that there is a definite range where that happens, but that range is extremely narrow. It's only about a 0.1 degree sort of full span. So what that means is if I want to make flat band twisted bilayer graphene, I have to fabricate my device such that the twist angle is about 1.05 degrees, 1.1 degrees plus or minus 0.1. That's a really small tolerance that I have access to. Okay, and you might say, well, we have precise micrometers and we can build stages, we can position things with near atomic, sorry, it can translate by microns, it can rotate by tens of degrees, et cetera. Okay, so these systems aren't stuck together when you make them. They have a tendency to move away from the angle you want them to be at. The more problematic sort of issue is that a new type of disorder emerges, or at least in my view, it's a new type of disorder that we might call Moiré disorder. So here's an STM image of twisted bilayer graphene. The atomic sites here are the bright spots of the carbon atoms, sorry. And if you look carefully, what you notice is that over a rather short length scale, it's only about 100 nanometers between these two unit cells. The two unit cells are quite distorted one relative to the other. This again is because there's very low interlayer bonding. And these systems tend to be under a fair amount of strain. So that strain can be relieved by distorting locally here and there a little bit the Moiré unit cell. In a sense, that distortion is equivalent to a local variation in the twist angle. And what we saw is that the band structure very rapidly depends on twist angle. So this was shown by Stefan's work, this flat band, or Stefan's, introduction. The flat band that exists evolves rapidly to the flat band condition and de-evolves rapidly away from the flat band condition. So it's not only that I have this 0.1 degree window, within the 0.1 degree window, things are changing extremely rapidly. So if I want to have a device have any kind of uniformity, it means that this problem has to go away. But there is not an obvious way to get rid of this problem because everything is not really well bonded out of plane. Or at least the question is there a way to get rid of this problem? That's sort of the question I want to address, probably for the rest of my talk. Okay, can we fix this? So it's important to maybe just take a moment and understand how do we actually make these devices. So we make them in a kind of a clever way. We start with some sheet of graphene. We cut that sheet in half. Now we don't need to know what the overall orientation of the sheet is, just that one half started off with the same orientation as the other half. Then I rotate it by some amount. Let's rotate it by the magic angle, and I place it on the other half. And when I do so, I can make a device that I'm nominally impart a twist angle of say 1.1 degrees. Okay, but as I said, the low interface, these things can migrate away from this angle. Okay, so how do we know that it's migrated by a little amount? How do we know that there's any uniformity or not? And how do we prevent this from happening? So the first thing is that it's rather challenging to know what the local moire disorder is. You have to do that through some kind of local scan probe, probably. So people can do this via STM, but those experiments are both challenging and limiting. You have to make a device that's amenable for STM, and typically those types of devices are not amenable for other things, such as making functional qubits out of. The other is that the other is that if you perform a transport measurement, for example, you end up averaging over all of this disorder. It's sort of hard to figure out necessarily what type and nature of the disorder that's present is there. Okay, so one of the things we developed in recent years was a tool that allows us to image these moire patterns basically in real time using a basic atomic force microscope. So what happens, it turns out, is that when you have these moire pattern bilayers, the domain boundaries that separate the unit cells of the moire pattern appear to have some piezo responsiveness. And we can measure this by doing what's called piezo force microscopy. And basically that involves bringing a charged tip nearby. We apply a bias to the tip, and we see how much the sample distorts as a function of applying a bias to that tip. And it turns out the grain boundaries or the moire boundaries have a higher response than the interior of the moire, and that allows us to image these things. So we can do this for twisted bilayer graphene. We can do it for any of the TMDs, and we can acquire now really beautiful imaging with the spatial resolution down to about maybe 5 nanometers or so. Okay, so this provides an opportunity to imagine that we can start to assemble our device, and while we're assembling it, we can take a moment and interrogate it. We don't have to take it all the way to finished device. We can sort of in situ ask, how is this device evolving? Is it disordered or not, et cetera? And we can really do that in the middle of the process that I described before. So imagine that I pick up some 2D material, I pick up some other 2D material, I can stop right here. I can literally turn this thing over. This is a photo image of our transfer slide. I can take this to my AFM and I can scan that. And I can say in mid sort of assembly, how are things going? And here's an example of an image like that. In this case, you can see that this moire pattern is very non-uniform. It's many hundreds of % change over just a sort of micron. So this allows you to do some kind of in situ real-time feedback. So that's a good start. We can reject devices we don't want, or proceed to devices we do want, or at least have a priori understanding of what our device is doing as we make it. The other thing that I want to try to do is figure out how to stabilize this angle. So I want to fabricate to an angle, and I want to stay at that angle. So one of the things I've said is that friction is low between these materials. That's because there's no bonds between the layers. It's all kind of van der Waals bonding. There's no chemical bonding. But the edges of the materials are a different story. What we've learned over time, and maybe I'll discuss at the end, is that if you have two lattice incommensurate 2D materials, friction can go very close to zero. They're called superlubrous sort of interfaces, but the edges can be very frictious. So if you have a lot of edge, it's a way to create a bit of glue in your system and kind of stabilize the angle. So we're pursuing that kind of idea now. Here's a sort of concept. We have a piece of graphene and we've cut two pieces out of it, G1 and G2. And it's hard to see here, but what we've done is add what we call, in our group, what we call whiskers to these systems. So there's a lot of really fine kind of comb structures that come out of each edge. And we do something a little bit clever. We etch this edge with a defined orientation, and this edge with a defined orientation that is an angle away from that. So let's call that 1.1, for example, if we target a 1.1 angle mismatch when we bring everything together. We take G2 and we place it on G1 such that these angles are aligned. That means the lattices are now necessarily misaligned by the angle that we decided. And we hope that these comb structures kind of lock everything in place. So that looks to be a fairly good strategy so far. So here's an example of what we can accomplish there. This is a kind of a large area device. I can't see if there's a scale bar here, but we can do this with devices that are sort of tens of microns on a side, and they look rather pristine. And indeed, if we look using our piezo FM technique, we can see that actually the moire lattice in this system looks unbelievably, by sort of our usual standards, uniform over very big areas. So this is a good start. I think this is something that we sort of trying to gain sort of control over and see if we can leverage this to more reliably make devices at angles that we actually want them to be at. Okay, good. So what I mentioned in the last part of this talk is asking, not only can we kind of solve this kind of somewhat technical challenge, but can we do more? Can we do new and interesting things? One of the things I keep saying is that a difficulty that we face is that there's low interfacial friction in these systems. But at the same time, that's actually possibly like really an advantage that we can leverage in these systems. Because the friction is low, that means not only can these things migrate and move around at will, it also means that we might be able to do that intentionally. There's basically no friction, and therefore we imagine that we can slide and rotate these materials one top of the other after we've made them. So we demonstrated this now a few years ago. We showed, for example, going back to the case of graphene coupled to BN, that we can define a structure where we have a graphene hall bar, that's the white outlines here. And on top of that, we transfer what we call a boron nitride rotator or boron nitride gear. And because the friction between the boron nitride and the graphene is so low, we can come in with an AFM tip and we can literally just rotate this gear around. And what that allows us to do is, in a device where we have electrical contact, we can measure transport in real time. After that device is made, then we can post-device fabrication alter it by changing the sort of BN orientation. So here's an image of that. This is an AFM image of such a device. What you see here now is just sort of false colored, the graphene as they showed here on top of that BN. And now if we come in with our AFM tip, we can mechanically literally just rotate this BN around. So you can see it's a little bit, baby's first steps. It's a little bit janky, but nonetheless, we have this degree of control. So now what we can do is, in this system, we can measure as a function of the twist angle of that BN, how that's modifying graphene. And if you remember, graphene coupled to BN has a central peak in resistance, and it has a satellite resistance peak. This is room temperature data. The electron side peak is a little bit diminished. That's typical in room temperature data for these systems. What you can see is that as we rotate this BN away from alignment, the position of this satellite peak is continuously shifting out. That's exactly what we'd expect, because the position and energy where that peak exists is related to the size of the moire wavelength, et cetera. So we can actually use that position to measure the angle. And what we can find is that with this technique, we can control the angle to within about, what did I say here? I can't see what I said here, but it's within about, about 0.1 degree precision. So that's fantastic. If we want to be in the business of making twisted bilayer graphene, one can imagine that this is the kind of technique that we might have access to that would allow us to do that. Okay, so more recently, we've done some more interesting things. We can rotate not just 2-layer systems, but also 3-layer systems. Here I'm revisiting the idea of graphene on BN. I can imagine that I place graphene on BN and I place it in such a way that the graphene is aligned to the bottom BN in this case. So there's a moire pattern that develops. And then I can ask what happens if I add another BN on top of that. So now I've got a BN on the bottom and a BN on top, and I can rotate. I'm going to leave the bottom BN fixed at 0 degrees, and I'm going to rotate the top BN. So what you see here is something really quite interesting. Again, I've got a moire pattern due to the top BN and the graphene, but I also have an interference of these two moire patterns. The moire between the graphene at the top and the moire between the graphene and the bottom, they interfere with each other and give me some kind of super moire structure. We can measure, again, transport in such a system. This is a very specific example where bottom BN stays fixed at 0 degrees, graphene is at 0 degrees, and we twist the top BN around. So if we do this, we measure the resistance at the charge neutrality point and the satellite resistance. And what we see is that the resistance at the charge neutrality point oscillates on a 60-degree cycle. It's really 120 degrees, but it's high, low, it's high in a 120-degree cycle, et cetera. Okay, we can measure the gap at all these points. And the one thing I just want to emphasize is that when the two BN layers, top and bottom, when they're aligned to each other, the gap is high. And when they're anti-aligned to each other, the gap goes to 0. And you sort of have to think through a little bit why this happens in this way. But in the end, what we're really doing when we're tuning this system is we're tuning the overall symmetry of the crystal. So this is something I didn't talk about previously, but one of the things that really dictates the properties of the material, one way to classify, one way to account for how the atoms' positions dictate the properties of the material through symmetry arguments. In this system, what we're saying is that we can rotate this system dynamically from being basically mirror symmetric, or I think it's inversion symmetric in this case, to non-inversion symmetric, as we make the BNs aligned or anti-aligned. And in one case, we have a gap. In the other case, we fully suppress the gap. Okay, so again, that's just sort of really interesting and sort of new level of control. Okay, so in the final few minutes, what I want to do is ask, can we apply this business to monolayers? So what I showed previously was we were rotating bulk BN, which we imagine we can get some purchase on and rotated on graphene, etc. So we devised a scheme that allows us to do this. As a cartoon sort of illustration, imagine I begin with BN and I begin with really monolayer graphene. And on the far right, I've got what we're going to call a graphite gear. So this is bulk graphite that I've just etched into a shape. And so what I'm going to do is place my monolayer graphene on top of my BN. And then on top of that, I'm going to place this graphite gear. Now, what's going to happen is the friction between graphite and graphene is low if the lattices are not aligned, if the angle is not 0. But if I align graphite to graphene, I basically just add, I weld the graphite to the graphene because it just becomes graphite plus one more layer. So in that case, I expect the interlayer coupling to be much stronger than it otherwise is. So I can begin with this system. I can come in with my AFM tip. I can start to rotate the graphite gear around, and it rotates freely. And it does so until I align it to the graphene. And now if I continue to rotate, what's going to happen is this graphite basically has larger friction to the graphene than the graphene does to the BN underneath. Now I can rotate this whole composite system. So now what this does is this gives me what we call in my lab a handle, a gear, if you will, to rotate basically this monolayer sheet of graphene. So does this work? This absolutely works. Here's a sequence of images where we've got monolayer graphene sitting on BN. We've added a handle like I've talked about. In this sequence, we use this handle to shift the monolayer graphene towards the edge of the other monolayer graphene. Then we use it to rotate. And what we're trying to accomplish here is to rotate to the magic angle of twisted bilayer graphene. So after we finish our sequence, we can image by PFM, the same technique I described before. And now what we see actually is that there's a beautiful moire pattern. It looks quite uniform. And if you're familiar with looking at these or you look carefully, you'll see that actually there are 2 length scales in this moire pattern. One length scale actually is coming from the graphene, 1 degree misalignment. And the other length scale is coming from the fact that in this particular case, the bottom graphene layer ended up being aligned to the bottom BN layer. So we actually see now this interesting sort of like interference of 2 moires again, in this case, graphene and graphene BN. Okay, but this suggests some really obvious sort of potential in terms of how we can control these systems and take really realize full control of all the sort of parameter space that's available. Okay, here's just some like highlight reels. Here's an animation of us taking this. This is really monolayer graphene, and we're just moving it around on a piece of, in this case, I think it's a piece of bore nitride. We can do this also with any of the other transition metal dichalcogenides. So again, if we're going to move WSC2, we use a WSC2 bulk, etched bulk as a handle, or we can deposit metal directly in that case, or any of the other kind of materials. And in general, friction is low, so we have the freedom to kind of move these things around. Okay, so this is great. The challenge is that what we've learned over time is that suppose we want to twist graphene to the magic angle. We can freely twist from 5 to 30 degrees with repeatedly and with very little difficulty and with high angle resolution. But if we try to twist between about 5 and 0 degrees, the problem is that actually the system wants to migrate all the way to 0. So it turns out that as you get to sort of like 0 degree, the system is strained. The moire pattern is resulting from the fact that the lattices are mismatched. And what that strain seems to want to do is drive the system to a configuration that relieves that strain. And the lowest strain configuration is like Bernal stacking. So AB stacking of bilayer graphene. So what we found is that if we try to rotate below about 5 degrees, the rotation tends to get away from us. It tends to rotate on its own once we start the process to 0. So, we're still trying to solve that problem. It's maybe we have some ideas about how to solve that problem, but for now, that's sort of where we're at. But one way we've addressed that problem is to realize the following. As I said before, friction is low. We've measured this directly now. We now know how much friction is being contributed from the bulk-bulk interference versus the edge bulk interference, and we know that edges matter the most. So we can think in a bit of a clever way about how to take advantage of that, and we do that in the following way. We imagine that now we have a long graphene ribbon. So now we've got a large amount of edge to bulk, if you like, and we're hoping that that edge is going to create a higher friction sort of scenario than otherwise. And what we can do is we can push on one edge of this, what we call a ribbon, or in my lab, they call it a noodle. So I apologize if I slip into that colloquialism. And we can imagine that we could, distort this. So we do this experiment, and absolutely we can do this. So here's the images, sort of overlay of 2 images before and after. So the straight is before, we take this handle, we kick on the edge of this, and we bend it into a shape. And the amazing thing here is we can, push this handle in place, bend the ribbon, we can remove the handle, and the ribbon stays bent. It turns out there's enough friction in the system to kind of hold its shape once we bend it. I wouldn't have necessarily predicted this, but that is in fact the case. Okay, so in this scenario, we get about a 15-degree bend. The amount that you can bend it, I'll show in a minute, depends on the aspect ratio of the noodle. But what we can do is we can interrogate locally, how is the angle of this graphene evolving relative to the BN? We can do that by measuring the Moiré pattern. From the Moiré pattern, we can do an FFT analysis, and that gives us a measurement of basically what the periodicity of the Moiré pattern is. So here's a movie that my student made, which is the analysis of the Moiré pattern converted. It's FFT basically. So the distance of these dots from the center is a measure of the Moiré wavelength, and you can see that it just varies continuously as we move up and down the noodle. So this tells us that this bending scheme provides a continuous way to change the angle. So maybe, can we get 1.2 and not 1 degrees, or 1.1 and not 0.9 degrees? That still is a bit of a challenge, but we can definitely rotate from 5 to 0 degrees and have a continuum of all angles in between those. Okay, cool. The bending mechanics is very similar to the bending mechanics of a simple beam. If you bend too far, the beam will buckle. It does this because you exceed basically the allowed strain deformation that you can put this beam through. So here's an example of that. It turns out that if you marginally buckle, so here is another sort of image of bending one of these nano, noodle beams or whatever. If you go just to the point of buckling, you can see it right where my mouse is. At the extreme, it starts to buckle, but not too much. You can undo that. So this is not reversing the image. This is pushing the handle to the left and then physically pushing the handle back to the right. So this is actually a reversible process. If you buckle too far, it tends to, I'm not exactly sure, it seems maybe it tears or something. It sort of becomes non-reversible, but there's a point where it is reversible. Okay, so we can do a little bit more analysis. Here's more detailed images of what those Moiré patterns look like as we move down this bent nanoribbon. From analysis of the Moiré, we can get a measure of what the angle is. And what you can see here is that the angle looks like it's going really linearly with position down this arc. I guess that's arc length. I don't know exactly how this is defined. So that tells you that you've got a continuous evolution. The other thing that you might immediately sort of think about, if you sort of pause for a moment, is that there probably is some strain in the system. So this is a beam. You imagine that it's going to be compressed on the inside of the beam, and it's going to be under extensive strain on the outside of the beam. And indeed, what we see is that if we look in detail at these Moiré patterns, these dots are kind of elongated. And further, the distance between opposing positions in the FFT are not exactly the same. They kind of change systematically. Okay, so we can look at that actually by looking at the Moiré pattern. The Moiré pattern actually is a rather nice local strain gauge, if you think about it. So here we can look at basically Moiré pattern as I move down the arc of some bent situation, or I can look at how the Moiré pattern develops as I move across the arc. So in a sense, we imagine that along the bent beam, we have basically varying angle, but at some kind of height across, it's fixed strain. Or if I cut across here, I'm at some fixed angle, but varying strain. And through kind of careful analysis of this problem, you can sort of calculate how you expect the strain to evolve in a simple way. And it turns out that our strain appears to be doing that. So I'll kind of skip to the end here a little bit. Here we've got some Raman imaging of a bent ribbon. What we see by sort of mapping the shift to the 2D peak is that indeed it appears to be that there's a rather smooth and continuous evolution of angle and strain in the system. And again, the Moiré pattern tells us that directly. So what I'm showing here basically is in the middle is along the neutral axis of this beam. What we see is that just visually, you can see the pattern that we measure in the Moiré is really a triangular pattern. That's what you would expect if there's no strain. And as we go to the extensive strain side or the compressive strain side, what you see is that that triangle gets distorted. And what we've done in this analysis here is to basically say, impose on this kind of like image a local kernel of a triangular pattern that we expect the Moiré to have, and measure how different is the sort of shape from that expectation, and from that difference we can sort of back out what the strain is. Okay, and this is all kind of very early days, so I don't have a complete analysis here, but it looks like basically if we correlate the Moiré measure of strain and the Raman measure of strain, there's an excellent correlation between these two. So we think we know exactly what's going on in these systems. And in particular, this image here is twisted bilayer graphene. So what we think is actually going on is we have really a beautiful continuum of strain and angle in this system. Okay, so the ability to impart strain gives us yet a new opportunity. I'm going to skip past this, but if you have a strain gradient in your system, that's a recipe to give a like a gauge potential or a pseudomagnetic field effect on the system, and you can exploit that to realize something you might call like synthetic magnetic fields, and see Landau level quantization even with zero field, etc. And this has been explored extensively in the past sort of decade or so. What I'm suggesting is that the techniques that I'm showing here might allow us to do this in a tunable way. So we might have access to sort of time varying magnetic fields in these systems by imagining that we can sort of actuate this bending in some controlled way. Okay, last thing I want to say, this is all fantastic, but it's a little bit, perhaps a little bit clunky. To get this noodle to bend or to get this thing to rotate, we have to come in with an AFM tip and mechanically sort of push it around. It's a rather tough process to go through. Eventually, we had the thought that we might be able to actuate this in some kind of non-contact way. Can we do it electrostatically? And there's a very simple experiment here, which is take one of these beams and put it into the middle of a capacitor and charge the beams. Now I can put charge on this by gating, and I can apply a potential across the capacitor. And I can ask, does this charged beam deflect in the presence of this potential? So here's an example of that. This is now an optical image. We made the device big enough so we could just image it in real time. So everything's kind of like run through a filter just so you can see the different parts of it. But just to orient you, this shape here is basically the graphene. It's equivalent to the shape here. And on either side of this is an electrode. What we're going to do is apply a finite bias to the electrodes. And we're going to apply separately a charging bias to the graphene. Okay, so if we do that, we can see that indeed we can get the graphene to deflect. So this is monolayer graphene in this case. And the reason it's cycling is in this image, what we're doing is we're cycling the bias. So we're turning the bias extreme positive to extreme negative. In this case, I think it's the actual charge. It's on the graphene that's cycling. Okay, great. So we have electrostatic motion. We're very excited about this and doing a lot of things right now to try to figure out how we can exploit this to do a number of things in real time. Stefan, I think I'm sort of probably a few minutes over now, so I can stop here.
Sure, it seems like you were starting to make your way into some of the questions people have been asking anyway. So Yuval, for example, was asking, related to this, how much strain would you need in order to start getting Landau level sorts of effects from these pseudomagnetic fields? Do you think that's within your range of?
Yeah, so the answer is that it's like order a few percent. So graphene will break at like something like 4 or 5% strain in the best case scenario. If you can get to like 1 or 2% strain, something like that, then you can get to Landau level of equivalent cyclotron gaps in your Landau level spectrum that are, let me think. So I think we calculated that the maximum strain that we've measured right now in our bent beam, I think it's about 1%. So sorry, the answer is a little bit complicated. So the actual conversion from strain to cyclotron gap depends on the strain gradient. So it depends on the precise shape of the thing. So I don't have a good answer in the moment, but for our bent beams where we know what the average strain is, the average strain is a few percent. We think we can get to about a half a Tesla, maybe as much as a Tesla in these systems. So that's not an enormous amount in this geometry, but that is a measurable amount. But we are conceiving of other geometries where we might be able to sort of push that up. We're limited by the breaking strain, which is say 5%.
I see. And do you have any measurements to that effect? Like, have you looked for the Landau levels?
So we've done some transform measurements that include basically two kinds of measurements. I don't have the data here, sorry. So let me just, so I can point to something here. We have a device sort of like this. And what we can do is, what we know is that we can basically, how to say this? So we can basically make a series of Hall bars. So the strain is sort of maximal at the tip here. And so we can sort of measure as a function of increasing strain down this bent noodle by making sort of side-by-side Hall bars. And there's some evidence that in that situation, a gap is emerging, whose origin we don't understand really in the case of graphene on BN. We actually bend it away from BN alignment and we see that a gap kind of emerges. A Hall bar is not the best way to measure the presence of Landau levels in this system because you actually expect that you have counterpropagating edge modes because basically the strain gauge couples to the K and K prime values in opposite senses. So what we have done also though, is we started the process of measuring basically Corbino response by imposing a dot array inside one of these bent noodles. And that data is too early to say anything meaningful about. What I do know is that absolutely the transport is varying as you move sort of through the system, but we're not exactly clear yet whether we're measuring something that really is like emergent Landau levels or not.
Wow. Thank you. Yeah, thank you for that. That's really interesting. Backing up a bit, so about 10 minutes prior to this, most of this strain discussion, Alpin had a question. That's something a bit outside of my expertise. So maybe they can feel free to interrupt or to vocalize the question in real time. But they're asking about the strength of the piezoelectric effect compared to with traditional materials. And in practice, is the piezo coefficient equal to 0 for bulk HBN and graphene, which are centrosymmetric?
Right, so that's a great question. So I didn't talk about piezoelectricity at all here, but we are studying this quite a bit. So it turns out that these layered materials generally are piezoelectric if in an even odd sense. So as was just indicated, you require that the lattice be centrosymmetric, and the lattice will oscillate from being centrosymmetric and not centrosymmetric as you go from like 2 to 3 to 4 to 5 layers, et cetera, right? So it turns out that like bilayer BN is not, 3-layer is, and so on. And what you, so people have measured piezoelectricity in these materials. They've done that by kind of conventional measurements. Typically, you're on a physical beam bending apparatus. You strain the material and you measure a potential that results, and that gives you a measure of the piezoelectricity. In general, the coefficients, if I remember correctly, are like order unity, whereas the coefficients for very good piezo materials, like these ceramics, are like orders of magnitude larger than that, tens or hundreds. I don't quite remember. Somebody should correct me on that. So in practice, as far as I'm aware, the piezo response that's measured in many of these materials does not compare favorably, you might say, with like the best performing piezoelectric. However, there are advantages that we have here. One is that we can imagine, for example, that we can do the same thing you do with conventional piezos, which is you can build the equivalent of a piezo stack. So in our case, we could imagine, for example, that we could have, say, few layer BN, which is piezo responsive, and pattern it with a bunch of electrodes, many electrodes in parallel. That gives you basically an in-plane piezo stack. And you can imagine that by applying potentials, you could get that whole thing to expand or contract. And it's almost certainly going to be the case that that would happen because the friction between that BN and the substrate that you provide, some lattice mismatched substrate, will have very low friction. So it might be plausible that actually you could do something like that. My answer is sort of this detailed because it's something we're trying actively right now. So you know, to be determined whether it actually works or not. But was there more to that question? Did I answer the question that was asked? Sorry, I can't see the chat right now. So
yeah, thank you.
okay.
Nice. Rob Cook had a question. It was concerning the effect that the whiskers have on your bulk measurements. He says that they look like they originated from a non-trivial amount of the original sample. Do you have an idea of how the whiskers, or maybe how these gears, like how these external attachments, might, like, are they far enough separated from the region which you're investigating or probing that
Yeah,
they wouldn't matter? And how do you know?
that's a good question. So the beautiful thing here, I don't know where that image is. Sorry. Oh yeah, it's back here. The beautiful thing here is that is, you know, the really nice thing about these 2D materials is that they're very like you can do a lot to them. Everything is sort of like that's what I'm looking for, disposable. So we can put these fingers in place. We can then add electrodes. That would be the beginning of, say, a hall bar shape. We want to do a measurement. And then we can just etch everything away afterwards if we don't want. So it's like a very forgiving sort of material. It's not like once you put it there, it's hard to change it. So in this system is quite clean, sorry. I can imagine that through, maybe I measure the moire pattern and maybe I identify that a little square patch here has a uniform moire of a wavelength that I want to study. And away from that, it does not have that same moire. I can absolutely, you know, define electrodes in the system, and then I can just carve away all the parts I don't want later, and then just measure the pristine part of this at the end.
How big would that region have to be? Does that depend on the sort of measurement you're making? Like a hall bar measurement, how many lattice lengths would you need?
I mean, there's different answers to that question. So there's some practical, like, lithography concerns. It's pretty easy to make a device that's about a half a micron on a side. But then there's also like mesoscopic concerns that you get to. If you're trying to measure transport in a device that's too small, you get dominated by sort of like resonances that are set up by the edge disorder and the bulk disorder landscape, et cetera. But if it's clean enough, then good question. One of the questions I might ask, maybe somebody has thought about, is the question we keep asking is that the moire pattern is itself has a well-defined unit cell. So if you can start to ask, like, what happens down at the single unit cell level, or, you know, start to imagine that you couple just a few unit cells together, can you start to sort of impose confinement considerations on top of the moire pattern, and so on? There's interesting questions that might arise from that.
Thank you. Wonderful. Do we have any more questions? I guess we're nearing the last few minutes of this question period. Yuval has another question. It's whether there's relaxation of the moire superlattice, if it's possible to measure it. I was curious about that too.
Yeah, absolutely. So what we do know is that I skipped a bunch of details here, but when I was measuring this is a good example of this. When we measure graphene on BN, graphene BN is not actually lattice commensurate at all. So one of the questions you might ask is, should you or should you not have a band gap in the system? One of the first answers that was given, theory answers, was if you imagine graphene and BN are coupled and you assume their lattices were exactly matched, then the two sublattices that Stefan introduced, A and B sublattices, would see different potentials. One would see a boron atom and one would see a nitrogen atom. And that would be enough to break the sublattice degeneracy of graphene and open a gap. But the lattices are not matched, they're mismatched. So an argument was made early on that if you put graphene on BN, over the whole area of the device, in some cases, the A sublattice is seeing boron, in some cases it's seeing nitrogen. If you integrate the whole structure, there is no sublattice symmetry breaking term. Therefore, you should not see a gap. So then eventually we measure the devices and see a gap. So where does the gap come from? The gap comes from the fact that these lattices actually do relax. The lattice mismatch imparts a strain, and that strain causes some relaxation. I don't have any images here. And that relaxation gives rise to, like, what is the shape of the moire pattern that we see?
Moiré lattice scale. For instance, there was the Steve Louis group and Feng Wang here. There's a joint theory experiment where they saw that in these hetero-bilayer TMD systems, strain and not like orbital hybridization between the layers, but strain itself is the dominating effect, which produces the Moiré potential that the parabolic electrons see.
Yeah, that's absolutely true. Also, what I'm trying to say is that in this case, if you were to look carefully here, so this is the Moiré pattern. This is like a unit cell of the Moiré pattern. What's happening in this scenario is that the graphene and the BN are basically commensurate at the middle of this pattern. The graphene and BN lattices both strain a little bit to accommodate each other.
Right.
But then when you get to the boundary, which is being imaged here, it's identified as the soliton boundary. That strain is being released by this sort of like bunching of the system at these edges. Exactly as you say, that physical distortion on its own can basically impart a flat band in the TMD systems. Some work was done there actually that showed that really beautifully.
In your systems, are you able to identify or map without STM topography, like out of plane buckling as well? Or are you kind of limited to measuring in plane strain effects?
The out of plane is difficult. So there are attempts that have been made. There was some great work also done by Mike Romey to try to address this issue. Part of the problem though is that it's a squishy system. So you have to be quite sensitive to the fact that as you try to interrogate the landscape, you might also be deforming the landscape at the same time. So you got to sort of figure out a way to deconvolve those two effects. Yeah.
Right. So it looks like we're probably at the end of the time. Lots of great questions. Thank you, Cory. Give you all a round of applause for the talk. I guess I'm the only one with my sound on. But,
okay, yeah, thanks for having me. Thanks everybody.
Thank you so much. I think now is the time where we're supposed to formally kick the professors and senior researchers out of the room and have a more intimate or close contact discussion with the postdocs and Berkeley grad students. So if you don't mind, Cory, sticking around for maybe another 10, 15 minutes, we'll see who sticks around and